Let me, how do I do this? Let me try to open a whiteboard. Okay, so first thing I'm going to show is let's use carbonate ion as an example to show you when to draw a double bond and when you don't need a double bond.
Okay.
So CO3, 2 minus, right? And then we calculate the valence electrons for carbon. Carbon has 4 valence electrons, right?
Okay.
Oxygen has 6 times 3, and then plus the 2 for the 2 minus charges. Then we have 4 plus, that's 18, right?
4 plus what?
18.
Oh, yeah, 10 and well.
And then we have 24 electrons.
Yeah.
Now, what we are going to do is carbon is a central atom in this case. And then we draw the oxygens.
You're just adding up the valence electrons, correct? Not
Here, yes. So here you need to add up all the valence electrons and then the charges here.
add
If
the
it's minus charge, then plus 2. If it's 2 plus, then minus 2 here.
Okay.
Yeah. So only the valence electrons, and especially for carbon, if you look at the periodic table, be very careful not to use the atomic number, which is 6.
Mm-hmm. That's what I do sometimes, and then I'm like, oh no.
I do that too, and then I kind of use the so I kind of think that, okay, the maximum number we usually use, maximum number is 8, maximum number is 8, and we don't use that actually for all the molecules that form that the one with the highest valence number of highest number of valence electrons would be 7 for halogens.
Yeah.
And then when I write carbon for 6, and I realize, oh, that something is wrong, it doesn't look right.
Yeah. Mm-hmm.
Because carbon is 3 atoms apart, 3 elements apart from fluorine. And that makes me realize, okay, this is not right.
So it would go basically like, isn't it like where boron starts, that's 3, and then 4, 5, 6, 7, right? On the periodic table?
Yes, boron is 3, you're correct. 3, 4, 5, 6, 7.
Okay, cool.
Yes. And then to the carbon dioxide here, and then you just draw all those 3 bonds here. And the first thing I would do is to just minus the bonding electrons. So 2 here, 2 here, 2 here. So I'm going to minus 6 bonding electrons, and I get 18 left.
Okay.
And 18, then I'm going to do this to complete the octet for the oxygens. 18 minus, and each of them needs 6 times 3. They're all identical, and therefore there's no electrons left for carbon here.
Okay.
Right?
Mm-hmm.
We have 2 left, then we can put the 2 electrons at the central atom, but now we don't have anything left. And if you look at this, carbon only has 6 electrons. Yeah, so we need to find 2 more from somewhere else. And this is when you have to consider forming double bonds.
Okay.
Yeah. And so I can form a double bond by just sharing this pair of electrons with carbon. And then you get a double bond here.
Okay. See, I was always confused because I thought you would just like take a pair off of oxygen and just put it on the carbon.
So you do take a pair off oxygen, and that pair will be shared between carbon and oxygen to form the second bond.
Okay.
Yeah. So then if you count for this oxygen here, it has 2, 4, and then 6 and 8 electrons. And carbon also have 2, 4, 6, 8 electrons.
Okay.
And then based on this structure, we can ask like how many resonance structures does it have, right? Because you can share this electron from this or oxygen or this one, or even this one. Therefore, it has 3 resonance structures. I'm not going to draw all of them, but then you can put a double bond here, and this becomes a single bond, or put a double bond here.
Okay.
If I can also ask you, for example, what is the geometry for molecular geometry for this ion here?
Would that be tetrahedral?
The
Or-
carbon.
Or is it trigonal? No.
It would be, so you count the number, first count the number of electron domains, right? You count the domains, which one count as one? So if you have a pair of unpaired, if you have non-bonding pair, that's one domain. So let me count this. So this is one domain. This is the second domain. This is third domain. And any bonding would be counted as one domain. So this is the fourth domain. So this oxygen has 4 domains. When you have 4 domains, then you have a tetrahedral geometry, right? And here, if you count for the central carbon here, so it has 1 domain, 2 domain, and this double bond is counted as 1 domain because they point to the same direction.
Okay.
So this is a third domain. Therefore, you have 3 electron domains correspond to a, I don't have it here. Where's my molecular model? So you have this flat trigonoplanar geometry.
Okay.
It looks like a triangle, right? So here you need to go to, am I sharing my, let me share my desktop here. So you go to this table over here, not this one. This table summarizes different from the number of electron domains to figure out the domain geometry.
Okay.
And then the bonding, the bond angles.
Okay.
Yeah, so this is the table to do that. And then this is an electron domain geometry. From electron domain geometry, you can predict the molecular geometry. Only accounts for those atoms bonded together to form a molecule. So in this case, and this table here shows you different molecular geometry that can be derived from the electron domain geometry. So this is linear, and what we just showed you is a trigonoplanar.
Okay.
Yeah, so if
because it's only got 3 electron domains.
Yes, when we have 3 electron domains is a trigonoplanar, and when we have 4 electron domains is tetrahedral. But then you count like how many bonding electron domains you have, not how many non-bonding domains do you have. When you don't have any non-bonding domains, meaning that all these electron domains are overlapped with orbitals of other atoms to form a bond, then the molecular geometry is the same as the electron domain geometry.
Okay.
Yeah, and in this case here, for example, it's only bonded to 3 atoms. So it has 1, 2, and 3 bonding domains, and here is 1 non-bonding domain in this case. Then we have a trigonopyramidal for this molecule. And for water, it is bent.
Yeah, bent.
Yeah. So this is the difference between electron domain geometry and molecular geometry.
Okay.
And when you answer a question like this, after you have put in your answer, always go back to the question to double check is asking about electron domain geometry or molecular geometry.
Okay, all right.
So double check on that, yeah. So going back to this carbonate ion here. So yes, this is when you need a double bond.
Okay.
We also have an example of tar carbon dioxide. We can take a look at that as well.
Mm-hmm.
And when you see the one with sulfur, it's more complicated. So I'm not going to ask you any question on drawing the Lewis structure for sulfur-based molecules.
Okay.
Because its number of electrons can go more than 8, and then it becomes more complicated.
Okay.
We do have one example for carbon dioxide, like why carbon dioxide, where is it? Formal charge. Oh, that's a previous chapter. Let me see. Open recent. I hope this is the one. I'm looking for the formal charge section. No, that's ionic bonding. Here's a formal charge here. All right, if you look at carbon dioxide, let's try to do this one. Annotate. So CO2, and it has, then we count a valence electron would be 4 plus 6 times 2. It's 16 electrons.
Okay.
Well, plus 4, 16, yes. And then, okay, first we're going to draw this, and then we have 16 minus 2 here, 2 here, the minus 4 bonding ones. We left with 12. Then 1, 2, 3, 4, 5, 6. 1, 2, 5. 1, 2, 3, 4. 5, 6. So 12 minus 12. Again, then 0 left.
Yeah.
So now we have 2 ways to share the electrons from oxygen. We can take one from this oxygen here, and we can also take one from this oxygen here, because the carbon needs 2 more bonds to complete the octet, right? And if we share from one from each of the oxygen, then we get this structure over here.
Okay.
But we can also share 2 pairs of electrons just from one of the oxygen and from a triple bond like this one.
Okay.
Right?
Mm-hmm.
That makes sense, right? And
yeah.
Now you have 2 structures. Now you have to use the formal charges to determine which structure is more dominating.
Oh, okay.
Yes. And the same thing for more complicated structures. If you need to do that going into other courses, then the formal charge is the way to determine that how exactly do they form double bond or triple bond.
Mm-hmm.
Yeah. So this one, then you calculate the formal charges. Formal charge is calculated by using the number of valence electrons. So we calculate the formal charge for each of the atom. So we take one atom, for example, I'll take the oxygen here. I'm going to take this oxygen, and let's calculate the formal charge. So oxygen, the number of valence electron is 6 for oxygen. Oxygen is right before fluorine. Fluorine is 7 and oxygen is 6.
Okay.
6 and minus half of the bonding electrons. Then we count the number of bonding electrons for this oxygen here. We have 4 for a double bond, right?
Mm-hmm.
2 for single bond, 4 for double, 6 for triple. So this is the second part. And then third part minus all non-bonding electrons. Then we minus non-bonding electron, we have 2 over here and 2 over here. So we have 6. And then we get a formal charge of 0 for oxygen.
Okay.
Yeah.
Okay.
For carbon here, for example, you don't have any non-bonding electrons, then here is 0.
Okay.
Yeah, and then you can calculate the one for rest of them, and these are the formal charges. And then we have this rules of when you have more zeros, then that would be the more dominating structure.
Okay.
Yeah.
So for the carbon, for example, the half of the bonding electrons, that would be half of 8, right? So you would get
Yes,
4.
exactly. Half of 8. Yeah, that would be 4. And 4
Okay.
minus 4 is 0. And for this exam, you just need to know how to calculate the formal charge.
Okay.
Mm-hmm.
Okay. Thank you.
Yeah, so that is how to determine when you need to draw a double bond.
Okay.
And another important one is, let me go back to the whiteboard. Another important one is the one with boron. So when you have boron, when you have this one,
Mm-hmm.
yeah. And this one, we count, and it would be the same for this structure or this structure. And why is that? It's because no matter it's chlorine, fluorine, iodine, they have the same number of valence electrons.
Yeah.
And their Lewis structure would be the same. Actually.
Okay.
Yeah. So we are going to use this one as an example. Let's actually use this one as an example.
Okay.
BF3. And then boron is 3, right?
Mm-hmm.
Boron is 7 times 3, and we have 24 electrons. Then B, okay, and then 24 minus 6, 246 is 18. And then we just complete the octets for all of the fluorines, and that will use up all of our 18 electrons. And now, and in this case, do we need to share any electrons to form double bond?
No, right, because only 6 valence electrons can bond to boron, right?
Yes, because it's boron, so it's happy with 6 valence electrons. And now, what is the molecular geometry for this molecule?
Trigonal?
Yeah, it's trigonal planar. Yeah.
Planar, okay.
Yeah, and its molecular geometry and electron domain geometry for boron are both
The same?
planar. They're the same.
Okay.
Yeah. And what would be the hybridization for boron?
I'm not sure.
That would be sp2. Now, speaking of hybridization, let's go back to the slides and show you a review of the hybridization. Let's go down here. Not this one, this chapter, hybrid orbitals. So this chapter, we talk about the formation of covalent bonds. So valence bond theory describes that formation of covalent bonds are overlapping of atomic orbitals. So if they overlap, they have an head-on overlap, I recommend you to watch this movie after the class. This movie. So it shows you when they come head to head, they are going to form a sigma bond. And then when you have pi orbitals, so when you have pi orbitals, oh, this one is a good one. So sigma orbitals overlap to form this orbitals can overlap head on to form the pi bond. And then the p orbitals, this is a p orbital, this is another p orbital. Then they can come together, overlap side by side to form a pi bond.
Okay.
So this is the pi bond. And when you have a single bond, then that single bond must be sigma bond. But when you have a triple bond, then it has one sigma bond and one pi bond, as was shown here. Actually, you have a sigma bond over here, and you have a sigma bond here. This is a sigma bond. And then these two domains make the pi bond.
Okay.
Yeah. So
and that's in one double bond, or is that in one triple bond?
this is a double bond.
Okay.
We use different color, but actually this is one bond. So for pi bond, it has two. The electron density is concentrated above and below this plane, this internuclear axis, and that forms one bond. It's like when you look at the, it's similar to when you look at the p orbitals. So one orbital has one lobe above it and one lobe below, and has a nodal point over here. And the same for the pi bond. So this is one pi bond. And when you have a triple bond, then it looks like this.
It's two pi bonds and a sigma bond, right?
Yeah, two pi bond and a sigma bond. So you see the sigma bond in here in the middle. Sigma bond is here, hidden in the middle. Then this is one pi bond. And the one going out and inward from the screen, this is the second pi bond. You can't see the one in the back. Yeah, this is a triple bond. Okay. And here's the hydrogen. And this is a double bond. One here, and this whole thing is a double bond. So this is double bond. Okay. Yeah, so these are some of the basics. Oh, yeah, because I was talking about hybridization.
Yeah, that's what I don't really understand is the...
So this is a formation of bonding. And then, so covalent bonds, according to valence bond theory, comes from overlapping of orbitals. But where is it? Molecular orbital theory, hybrid orbitals, here. Hybrid orbitals is in some cases that the bond formation cannot be explained by just simple valence bonding theory. Like this one, it doesn't have any, this is beryllium. So if you look at this electron configuration here, it doesn't have any unpaired electrons to form bonding, because when we form bonding, so one unpaired electron from this atom is going to overlap with another orbital of this atom containing one unpaired electron, and then they can share or hold hands. The electrons from both atoms can hold hands together to share, right?
Yeah.
In this case, you don't have any unpaired electrons. Now, then we have hybrid orbital theory that was developed, so that you excite one of these electrons to the hybrid orbital. No, not hybrid orbital yet. So you excite one of the s electron here to the p orbital over here and end up with this configuration. Now you have unpaired electrons. But two electrons are on different energy levels. And in this case, if one is from this bond, one from this bond would have different energy levels, and which is not the case because these two bonds are identical. Therefore, we are going to do a hybridization. So we combine this s orbital with this p orbital to form an sp hybridized orbital. It's labeled as sp because it comes from combining one s orbital with one p orbital. And now, after the hybridization, these two orbitals will have the same level of energy.
Oh, okay.
Yeah. And so we rewrite it like this. Let me clear all the drawings so you can see it better. So we kind of combine these two. Now this two has the same energy, and the remaining two p orbitals still have the same energy. Now we have one s orbital, the sp hybridized orbital, and two p orbital. Now each of these hybridized orbital can form a single bond, covalent bond with the unpaired electron of fluorine.
Okay.
So this example, you can see it over here. This is the same beryllium. beryllium, F2. So this is a beryllium, and this is how they hybridize to form new orbitals. This is hybridized orbitals.
Mm-hmm.
So if you have two atomic orbitals to hybridize, they're going to form two hybridized orbitals. The number won't change. So this is how the hybridized orbital look like. And then they share the electron with the p orbital of fluorine. And on this side is fluorine, and you form.
Oh, so the two p orbitals are atomic orbitals, where the sp one's a
Hybrid.
Okay.
Hybrid hybrid atomic orbitals, yes.
Okay.
Yeah. If you look at this, so this is how the orbitals originally look like. So originally, the s orbital for beryllium, so this is beryllium, this is originally how the s orbital looks like. And this is originally how the p orbital look like.
Okay.
Now they are going to overlap, they are going to hybridize to form one orbital with this shape, a big lobe and a small lobe, and the second orbital of the same shape, but pointing to the opposite direction.
Mm-hmm. Okay.
Well, what you're seeing here is just overlap of these two, or superimposed structure. It's only showing the big lobe. It didn't show the small lobe, but it's there.
Okay.
So these represent two orbitals.
Mm-hmm.
But different from this is just one orbital. Yeah, so if you look at after hybridization, what it looks like, then you still have the s orbital there, in there. And originally you had 3p orbitals, right?
Mm-hmm.
Something like this, 1, 2, 3. But then after the hybridization, what do you have will be, well, you still have one s orbital left. That is 1s. This is 1s. But this 2s, so what I draw here is 2s. So 2s is going to hybridize with one of this, so it disappears. Actually, let me also just remove this. So let's just ignore the 1s for now. Just look at the 2s. After the hybridization, what's going to get is this 2s is going to hybridize with this p, for example, and you're going with one orbital, two orbital. So this is sp, this is also sp, and then you still have two p orbitals left, right?
Mm-hmm.
You still have the p orbital here and p over here.
Okay.
If this is Z, I can draw this, so you have still px and py left, and with two sp orbitals. Okay. Yeah, this is how they hybridize. And in terms of, and then what's important, I'm going to skip the sp2 and sp3 over here. But in terms of how to use this, one important thing is to determine the type of hybridization.
Mm-hmm.
Yeah. So how to determine the type of hybridization is you are going to use this table here. First, it would starting from a molecular structure, right?
Mm-hmm.
Then you draw its, then you need to draw its Lewis structure. And then determine the geometry for the non-molecular geometry. You have to determine the electron domain geometry for the central atom. And if the electron domain geometry is linear, meaning that it only has two electron domains, so two electron domain, linear geometry, then it is an sp hybridization. So you have sp hybridized orbital forming bonding with the two fluorine atoms. And if you have three electron domains, the geometry will be trigonoplanar, right?
Mm-hmm.
And to form three hybridized domains, then you need sp2 hybridization. So one s orbital mixed with two p orbitals in order to get 3 electron domains here. And then you have a trigonoplanar geometry. And then moving on, if you have, for example, carbon, and you draw the Lewis structure, you'd see, okay, the carbon has 4 electron domains.
Mm-hmm.
And then we need an sp3 hybridization in order to get 4 domains. And the geometry would be tetrahedral.
Okay.
This is how to determine the hybrid orbitals.
Okay.
Yeah. Okay, now let's go back to, I see that you see another person joined. Clear all drawing. Jazeel? Did I pronounce it right? Okay, what I'm going to do, yeah. Hello, did I pronounce your name correctly? Okay, so you can, if you have questions, you can unmute yourself and then just ask me. We only have 3 of us here, so feel free to ask me any questions or interrupt me. Now what I'm going to do, let me just stop this recording.